Hi. In class, you've seen many theorems and rules to compute probabilities. The sum rule, the complement rule, the Morgan's laws. And in this example, I want to show you how you can use these rules to compute probabilities. So in this case, there are a few things that are given. We know that we have two events, A and B, and we know that the probability of A union B is 0.7. We know that the probability of A is 0.4, and the probability of the union of A complement and B complement is 0.8. And what we now want to obtain is, what is the probability of the event B? Now, let's see how we can determine that. First of all, we know what the probability of A union B is, so maybe we can use the sum rule. So recall that the sum rule says that the probability of A union B is in fact the probability of A plus the probability of B minus the probability of the intersection. So a few things we already know. We already know what the probability of A is, 0.4. We already know what the probability of A union B is, 0.7. And we're looking for the probability of B. So if we somehow can find the probability of A intersection B, well, then we're done. Then we can compute the probability of B. Well, let's see, how can we determine the probability of A intersection B? That's where we will use this final statement here. And in fact, we're going to use the Morgan's laws. Because one of the Morgan's laws says that the probability of A complement union B complement is actually equal to the probability of A intersection B complement. Okay, so we're already a bit closer to obtaining the value of the probability of A intersection B, but we still have this complement. So how do we get rid of that? Well, of course, with the complement rule. And the complement rule tells us that this probability, the probability of the complement of A intersection B, is actually 1 minus the probability of A intersection B. Okay, so now we're almost done because, we know that the probability of A complement union B complement is 0.8, and that was a given. And this is apparently equal to 1 minus the probability of A intersection B. And so if 1 minus the probability of A intersection B is 0.8, then the probability of A intersection B must be 0.2. And so we can determine now, well, this means that the probability of A intersection B is 0.2. Okay, so now we can finish up. Again, we will use the sum rule that we already wrote down. And let's just plug in all the necessary values. I've written down the sum rule once again, and let's see whether we can use it now to determine the probability of B. Okay, so the probability of A union B was 0.7, and that was given at the start of this exercise. Same is true for the probability of A. Now let's take a look. We saw at the beginning that the probability of A union B was 0.7 and the probability of A was 0.4. The probability of A is 0.4. The probability of B, well, that's the one we are looking at, the one we're trying to find. And the probability of A intersection B, we just determined, is 0.2. So what we obtain is a very simple calculation. So we have 0.7 on the left. If we bring the 0.4 to the left-hand side of the equation as well, and the 0.2, then we obtain the following. So this means that 0.7 minus 0.4 is 0.3, plus 0.2 is 0.5. So this is indeed the probability of B. Let's take a look at one more example, and here it will be convenient to use a Venn diagram. Again, two events, A and B, and what do we know about these events? Well, first of all, we know that A intersection B complement has a probability of 0.4, and we also know that B has a probability of 0.5. The question is, what is the probability of the intersection of A complement and B complement? Here too, we can use the Morgan's laws. We already used one of them in the previous example. Let's use one more for this one. Because the other De Morgan's law tells us that the probability of A complement intersection B complement is in fact the same as the probability of A union B complement. And again, if we use the complement rule, then this tells us that this probability is actually equal to 1 minus the probability of A union B. Okay, so if we can find the probability of A union B, well, then we're as good as done. Okay, let's see, how can we determine that probability? Two things are given. Let's take a look at the first one, the probability of A intersection B complement. What exactly is this event? Where is it located in the Venn diagram? Well, it contains all outcomes that are in A and not in B, because it's the events that are in A and in B complement, so not in B. So where is this event located in the Venn diagram? It's exactly this part right here. All outcomes that are in A, but not in B. Then we have the event B itself. Well, that's clear. That's the one over here. And this event has a probability of 0.5. Now, I think you can already see that this means that the probability of A union B has a probability of 0.9, the sum of 0.4 and 0.5. And actually here, we do kind of use the sum rule, only in this case, since the red event and the blue event do not have an intersection, well, in this case, we can just say that the probability of A union B is equal to the probability of A intersection B complement plus the probability of B. And so in this case, there is no third term. Usually there is in the sum rule, because these two events, the red event here and the blue event here, event B, do not have an intersection. Okay, so we find that the probability of A union B is 0.9, so 0.4 plus 0.5. Okay, this means that we're done, because we were looking for the probability of A complement intersection B complement. We already obtained that this, because of the complement rule and the Morgan's law, must be equal to 1 minus the probability of A union B. And we just found out that the probability of A union B is 0.9, so this must be 0.1. So that's the answer that we're looking for. The probability of A complement intersection B complement is equal to 0.1.